So today we're going to talk about section 9.2, which is on power series. So we're going to start out by just talking about the definition of a power series. So let's start with a definition. So definition of a power series is that a power series about a point x equals 0 is a series of the form we say this is the sum ingoing from 0 to infinity of c sub n times x to the n. Now, if I were to write that out the long way, it looks something like this. It would look like some c0 plus c1 x to the first plus c2 x squared plus c3 x cubed plus and so on out to infinity. So this is what we call a power series about x equals 0. And one thing that you can notice about a power series about x equals 0 is if you plug in the value 0 for x, so we've got these x's, and if you plug in x equals 0 for all the x's, you're just left with a nice constant, that first term. So if you plug in zeros in all these spots, you just end up with your constant C0. So that's why we call it a power series about x equals 0, is because if you plug in 0, you're just left with the first term, which is some constant. Okay, so let's move on here. Now we can talk about a power series about another number. So let's write down another definition real quick. So definition, a power series about some other point, let's say in this case we're calling it x equals a, is a series of the form we could say sum n going from 0 to infinity of now we say it's c sub n, which is the same as last time, but now we're looking at x minus a to the n. So if we were to write out a few terms of this series, it'd look more like this. We still start with c sub 0 plus c1 times x minus a to the first power plus c2 times x minus a squared, and if I wanted to keep going, plus c3 x minus a cubed plus and so on. Okay, so the only real difference between a power series centered at 0 and a power series centered at a is that when you plug in 0 for x in a power series centered at 0, you just get a constant, the leading term. If you plug in a to a power series centered at a, notice if you plugged in a for x, then all of these terms would just become 0, and your power series just boils down again to the constant C0. Okay, so we've got a power series centered at 0, and we've got a power series centered at A. Now, something that I will kind of bring up really quick is, what's the point of power series? In some sense, what we love about power series is they're just infinitely long polynomials. And infinitely long polynomials we like polynomials. We like polynomials when we take derivatives. We like polynomials when we take antiderivatives. So thinking of a function as a polynomial is often where we want to be. So let's look at a few examples of these power series and kind of see how this works. So a quick example here is, let's say that we had the sum n going from 0 to infinity of x to the n. All right. Let's write out a few terms of this power series just to see what it looks like. And so we get x to the 0 power plus x to the first plus x squared plus x cubed plus and so on. And if we were to simplify that down a little bit, I guess, we could just write it as 1 plus x squared plus x cubed plus and so on. Now, maybe I'd like to ask the question, well, does this thing sum up to something? And the answer is, well, it depends. This is different than anything we've done up to this point because instead of having a nice power series of numbers, now I have a power series and I'm adding x's up. So how am I supposed to figure out if it adds up to something? Does it converge? Does it diverge? Well, when I ask what this thing sums to, I'd say if it sums up to something, what would it sum up to? And so I'd use just my normal methods that I've learned in the previous chapter. When I look at this power series, and I look at this 1 plus x squared plus x cubed, what I notice is every time I'm multiplying to get to the next guy, I'm multiplying by the same thing. I'm multiplying by x every time. And so I recognize that this is a geometric series. And geometric series converge sometimes. When do they converge? Well, they converge if r, the thing that I'm multiplying each time by, or the ratio to get to the next term, when r, this converges, if the absolute value of r is less than 1. Well, in this case, our r is x. So in our case, that's if the absolute value of x is less than 1. This thing would converge. Okay, and then the question is, what does it converge to? Well, we know that geometric series converge to a over 1 minus r. In this case, a is just the first term of the series, which is 1, over 1 minus, well, r in this case is, we said that r is equal to x, so 1 minus x. So if this converges, which is only when the absolute value of x is less than 1, then we know what it converges to. It converges to 1 over 1 minus x. Okay, so this is a great example of, we have a nice geometric power series. It has x's in it. That's different than anything we've seen before. But we can still figure out if it converges or diverges. Even more than that, we can say for what values of x does this thing converge or diverge. So this thing converges if the absolute value of x is less than 1, and it converges to 1 over 1 minus x. Now, if the absolute value of x is greater than or equal to 1, then it just diverges, and we don't care, so to speak. Okay, so that's first example. Let's look at another. So let's take the following. So let's look at another example. Let's say that we have the sum in going from 0 to infinity of negative 1/2 raised to the nth power times x minus 2 to the n. All right. So if we wanted to, we could write out a few terms of this series. We could write this out as, well, if n is 0, then I've got negative 1/2 to the 0 power, which is 1 times x minus 2 to the 0 power, which is also 1. Then plus, I get negative 1/2 to the first power times x minus 2 to the first, plus negative 1/2 squared times x minus 2 squared, plus, and so on. Okay, so let me rewrite this a little bit. I've got x minus 2 to the 0 power. That's just 1. Then I've got negative 1/2 to the first times x minus 2, which is minus 1/2 times x minus 2. Then I've got plus 1/4 times x minus 2 squared. Can we guess what the next one would be? It would be minus 1/8 times x minus 2 cubed, plus, and so on. Okay? So we're starting to see that there is a pattern, and again, this can be written as a geometric series. But the key to figuring out, so does a guy like this, does this converge? Does it diverge? Well, it all depends on r, right? We know that it will converge if the absolute value of r is less than 1. What is r in this case? What do I multiply by every time to get to the next term in the series? Well, in this case, our r is equal to negative 1/2, because we multiply by negative 1/2 every time to get to the next guy in the series, times x minus 2. So r is negative 1/2 times x minus 2. And we know that this thing will converge if the absolute value of negative 1/2 times x minus 2, it will converge if that value is less than 1. Okay? In other words, that means that negative 1 is less than negative 1/2 times x minus 2, which is less than 1. I can solve that little inequality, and I would get that 2 is greater than x minus 2, which is greater than negative 2. And now I could add 2 to both sides, all sides, and I get 4 is greater than x is greater than 0. So that means that this thing will converge if 4 is greater than x is greater than 0, and it will diverge otherwise. Okay, so if x isn't in that little range, it diverges. If it is in that little open interval, then it converges. Now, this is the type of problem we're getting into. We're trying to figure out, where do these power series, where do they converge? And where do they diverge? So we need a little bit of a definition here. So let me write down a definition real quick. So let's talk about a radius of convergence. When we talk about a radius of convergence, all we're really talking about is what's the interval over which this series converges or diverges. So let me write down a quick definition. So 3 things can really happen. So 1, there exists a number we'll call it capital R, such that the series diverges for all x such that the absolute value of x minus a is greater than r, and it converges for all x such that x minus a is less than r. Okay. Now, so this is what we typically talk about as a radius of convergence. And what we're saying is if you're within some radius of the center, so remember we talked about the center of a power series, that it can either be centered at 0 or it can be centered at A. And this is saying if you're within some distance from the center. So let's just draw a little real line, and we'll put the center in here. This is A. And what we're saying is if I move R away from A, so this is A plus R, and if I move R away from A on the other direction, A minus R, then in this interval, the power series converges for all those x values. If you're outside of the interval, if you're out here, or you're out here, it diverges. And so the question is, what about at the endpoints? Like, what about at exactly the point A minus R and exactly the point A plus R? Well, then we don't really know. And we need to test something. And we need to test to see, does it converge? Does it diverge? Now, that's the first thing that can happen with radius of convergence, is you get this number capital R, where if you're within R of A, it converges. If you're outside of R, it diverges. So here's my, in here, it converges. Out here, it diverges. Okay? That's the first thing that can happen. Let's talk about the second thing that can happen, is we can, the series can converge absolutely for all x values. Okay, so this is when you compute your capital R, so to speak, and you compute that capital R is infinity. In other words, capital R is infinite. That's the second thing that can happen, is it just could converge everywhere. So it can converge in a little open interval around A. It could converge everywhere. And the third thing that could happen is the series converges at x is equal to A and diverges everywhere elsewhere. Okay, so three things can happen with radius of convergence. Either we've got this small little radius of convergence where it works, and we saw two examples of that in the two geometric series I showed you. The second thing that can happen is it could just converge everywhere, and the third thing that could happen is it converges absolutely nowhere except the center point. So the question is, how do you figure out which one's which? Well, that's where we go back to the previous chapter and we use all of our tests, the ratio test, the root test, limit comparison test, integral test. Use these tests to see where does the series converge absolutely. Once you know if it converges absolutely everywhere, well, you're in case 2. If it converges absolutely nowhere except the point x equals a, which, by the way, it always converges at x equals a because that's the center, and everything just goes to 0 except that first point. Or it could be kind of a unique interval, and that's where we call it converges on some interval of convergence. If you find that this interval of convergence is finite, then it's in the first case. So now you can watch some examples that I've got for you to see exactly how this works out.